Okay, hi everybody. So, yeah, as Tanmoy said, I'll be talking about today building and connecting artificial atoms for quantum computing, right? So before I tell you a little bit about what are artificial atoms and what I mean by them, we'll have to talk about what are normal atoms and how we can use normal atoms for quantum computing. So part of my talk will be about quantum computing with normal atoms, about how the quantum mechanics can help us design these atoms and understand them, right? And after that, I'll talk a little bit about how we can connect them and some of the big challenges that we are facing with these artificial atoms in terms of developing quantum computing, right? So for those who have attended my gossip talk like a few weeks ago, I'm going to run through a little part of that. We'll actually be taking those ideas again, and then I'll be building on those things, right? So just to start with, so what is basically computing? Before talking about classical quantum computing, let's see what is classical computing. Classically, we encode information in binary format, right? So when we have a normal, like in decimal 1257, if you have to write it in 1 and zeros, you'd write it in this way: 1001110111001. Okay, and the way you can encode that information is into binary information, between 0 and 1 physical system. So for example, it could be like on a CD, it could be basically like a dip would be 0, and the little hill here would be like a 1, and that's how you encode the binary information. For computation, this is for storage. For computation, you actually store them in transistors. So basically, you have this device that actually either has a current that flows or doesn't flow, right? Either, depending on the gate that you put on it, you'll either get a current or no current. So then your 0 becomes like a current that flows, and your binary 1 becomes current that doesn't flow. Okay, and so you can build basically a computer and do computations on these classically, right? So quantum mechanically, things are a little bit more complex. The fundamental idea is that objects can be in superpositions of different states, any different state. So instead of having either 0 or 1, suddenly you can get quantum mechanically, if you manage to control in this kind of system, you'd be able to create superpositions of those, where the system is neither in 0 nor in 1, but in a kind of superposition of both. Okay, because these states have a different nature, and we manipulate it in a different way, we have this little bracket notation that we use around them that I'll be using in this talk. This is to basically designate these quantum states, right? The normal classical states have nothing, but the classical quantum states have that. And so here you can get, let's say, a superposition. How do we write a superposition? Basically, we'll just do 0 plus 1. So we're just saying it's 1 plus 0. It's like, it means that we are in both systems at the same time. And this basically is what we call a superposition of states, right? So initially, when people started talking about quantum computation, they didn't really think about computers. They were thinking more about simulations, right? So there's a famous quote by Feynman which says that nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. Okay, and the idea is basically, if you can just map your real system, your real physical system, to a quantum system made of bits, then you can simulate, you can just reproduce the dynamics of the system you're trying to emulate, right? And that was kind of the initial idea that Feynman had when he was talking about trying to make a quantum computer with, quantum systems. But at the time of Feynman's quote, that was more than 15, 20 years before we were even able to control these quantum systems. We knew about quantum mechanics since very long back, but we had never controlled quantum mechanics. That means we had never, let's say, created, been able to excite one of the excited state orbitals of your atom and kept the atom in that state, right? We had been able to excite some orbitals and then seen some, light coming from the atoms. We could manipulate, we could kind of play around with the quantum. We knew it was quantum. We had proof, like the double slit experiment, which shows that if you, I'll just show just after that, which proves that we have superpositions, but we were not able to control it in a way that would allow quantum computing. Okay, so the people and physicists at the time started to try with a simple, most simple atom, right? So they were trying to create some states that they would be able to control and manipulate. At this time, they didn't know how to do it, and they had not achieved that. Okay, so that's basically quantum computers. So to understand, how we can use an atom, and what the physicists finally managed to do by, by the year 2000s, is basically we have to understand the quantum mechanics of the atom. So one of the fundamental principles is this wave-particle duality that you would have heard about. So one of the aspects, the points is that, for example, if we take light, light is a wave. It's not just a particle. And that you would have heard, you would have known this from school, right? You have the electromagnetic spectrum, and depending on the frequency, it corresponds to a different system. So radio waves, for example, have this very large wavelength, right? They're all the same thing. It's electromagnetic radiation, but it just has different frequencies. Now, microwaves, right? These would be also electromagnetic radiation, but at different wavelength size. And then you'd have light waves. So the light waves would have like another wavelength. It's a very, very narrow spectrum over here. And each different frequency will correspond to a different color. So this would be light wave, but they're all the same thing. They're all electromagnetic radiation. It's basically light as a wave. Okay, so all basically have these kind of oscillatory nature in vacuum, and their wavelengths, which we call lambda, is basically how far apart are these peaks. Okay, by the way, do ask questions and interrupt me if you want. We can also, I can repeat the questions for the online recording. So how do we know, though, that they're a wave? Like, what is the proof that we have? Because this is quite abstract. It's not obvious light is a wave, right? So to understand wave properties, imagine, for example, somebody creating like a little wavelet on the rope by just making this movement. And here the rope is attached to the wall. So here you have a wave that's actually propagating right. Now imagine, like I'm showing over here, that the wave there are actually two wavelets, one propagating in this direction and one propagating in this direction. Then what happens, as they move together, they collide, they'd form, and they'd form a wave with an even larger amplitude. They add up. And after some more time, they'd actually split away again. Okay, this is known as interference, and this is known in particular as constructive interference. Right? Now what happens if I have a negative amplitude and positive amplitude, and these two waves collide? So what you will see is that they actually cancel out completely. They disappear. The wave disappears. But if you wait for some longer time, and they come. So that's the principle behind this, is the linearity of the wave equation for the physicists, and the fact that you have a superposition of solutions. So this is called destructive interference. It's nice to illustrate this with water. If you do this experiment where you have like a big plastic ball and you make it oscillate in the water, it's going to create these ripples, right? You must have seen that with a stone just falling in the water. Now what happens if instead I'm actually using two of these, and I'm actually creating ripples at the same frequency like this in the water? So I'm going to get two of these, and you'll see that there's an interesting pattern that is going to emerge of making this oscillation. And this is basically an interference pattern. So you can see that here, there'll be like a line of destructive interference where the waves actually cancel. It's flat. And here, you see that there's constructive interference where basically you get these higher amplitudes. So that's constructive interference. So that's for water. And the other property, so that's interference, right? The other property of light, which is also something that's important, is what happens when a wave goes through a narrow opening. So if it goes through an opening that's large enough, like this, it just goes through, no problem, right? What if actually the light goes through a narrow opening? If it goes through a narrow opening, then this light actually gets squeezed in, and it actually then starts to propagate in all directions, you see, in this way. So that property is known as diffraction. Okay, wave spreads in all directions when it is squeezed into a narrow opening. Okay, wave is made to go through a narrow opening, it spreads in all directions, this is known as diffraction. So what about light? So these are the defining properties of what a wave is. Now, this is the famous, this is the double slit experiment. The idea is I have a big screen. In front of it, I have like a mask. And on this mask, I'm going to send some light. Now, for the non-physicist over here, what do you think am I going to get when on the back screen over here as I sent my laser lights? Okay, so these should be close by and the laser should be sending straight rays, but it doesn't matter. What will happen? What do you expect on the screen over there if I'm sending laser light in those two holes like this? Any ideas? Yep. So you mean something like this? Yeah, so that would be what happens if light was a particle, right? But the point is this is not what happens. This is what you would have guessed, right? The rays go through and they just form the same pattern on the wall. And the point is, instead what happens is this. Because light is a wave, right? It actually propagates like this as a wave all the way to the double slit. The wave reaches these slits, it gets diffracted because it's squeezed through this narrow opening, which means that from these two ends, now these two behave like sources. They start emitting the radiation, and you end up with this complex interference pattern in between, in the same way exactly as we saw with the two balls of plastic in the water, right? You can see, if you actually study this a little bit, we can see this line of destructive interference that I showed you for the interference in the water, right? So light propagates as a wave. But that's not the whole story, right? And we all know that, light can also be a particle. So, okay, imagine this light bulb, it's sending this waves of light outside. But then take an observer, all right? And that observer, so the particles of light are called photons. So the photon is going to impinge on your retina. When it goes on your retina, it's basically going to there'll be some chemical reaction, and that photon is going to get absorbed and then triggering a current. So here, the light is actually behaving like a particle, right? So localized, absorption of your energy inside one molecule of your eye, and that creates this. So this light here is an everyday example of how light is particle. Okay, so that's all nice. This is the quantum mechanics illustrated for light, right? So it behaves sometimes as a wave and a particle. But we want to understand the atom. Okay, the atom, to understand the atom, we need to understand the electron, right? So what about the electron? Well, it turns out, okay, so yeah, I was just saying wave. Can you say? Yeah. Okay, okay.
Why does that prove that it's why should one be convinced that it is particle?
Well, by particle we mean localized. Something that is really at a certain point in space. So the moment there's an interaction with the retina is a small object, right? And that...
Yeah, why can't we still think of it as a wave then?
Why can't we still think of it as a wave? Well, see, if you look at...
I think with the double slit experiment, right? The slit is too wide,
yeah.
Only what he said.
Yeah.
And smaller and smaller, you will see the diffraction pattern.
Right.
Right. So I think the same thing happens with the eye, right?
Right. So I mean, here I'm more. I'm talking more about the. See, in the double slit experiment, what happens is you would. Still, again, it's hard to say. Yeah.
You will only see those two. What we thought we would see.
Right.
But if it's narrow, it becomes at the wavelength of that line. Then it splits up into the pattern.
Right.
Right. I think here it's the same thing, no? Like this.
Well, so in double slit experiment, before you see anything, it will always be a wave, more or less, right? Even if it, yeah. Sushant, maybe you.
If I can add to that. So I think it has to do with the mechanism by which light is detected in your eye, because in your rods and cones you have certain molecules, and the light has to impinge on those, excite them, de-excite them, etc. So that requires that light be explained as a particle rather than as a wave.
So basically, light would have a certain amount of, we know how much energy has a photon, right? The particle we have the theory tells us what what the energy of a photon is. And you know that you need exactly that energy to be able to excite, let's say, one level of that molecule that is then going to trigger that whole chainy biological effect that is going to create the thing. So you know that in order to get this phenomenon for this phenomenon to happen, you will need to have the full photon to get absorbed, right? So it cannot be that it's only part of the photon that get absorbed, like 1/1,000,000th of the wave that is just oscillating on your retina and just creates the signal. It has to be the full photon in some sense. And experiments have shown also that, you know, if you do it with a single experiment and you just measure you know, the photon, you will see that the whole photon gets absorbed. It disappears everywhere else. We'll talk about this a little bit as we move on about this aspect, right? Of what it means to be a wave. Yeah, that's a bit the problem here. At this point, I have not explained what is a wave, you know, what is the meaning of this wave. So it's a bit hard to explain what happens quantum mechanically when we talk about wave-particle duality. So I'm getting there. Okay. So for now, take my word for it. I'll be going a little bit deeper in this. So wave can interfere with itself. So the point is the electron in any object in the world also has a wave aspect. So the wave-particle duality applies to anything, okay, including the electron. Any particle has a dual wave-particle nature. Okay, so that's just an illustration. You have an electron that sometimes behaves like point particle, sometimes behave like a wave also. So more generally, this is a theory that Louis de Broglie developed around 1924. Any object has a wave, and the wave length of that object of that wave is going to be given by this expression, right? So h here, okay, wavelength of the matter wave, okay. So yeah, so this is Planck's constant. This is basically the constant that gives you the scale of the size of the quantum, more or less, the scale of quantum of the quantum. And it's a constant, very, very small constant, 10 to the minus 34. It kind of gives you the scale of these objects. Okay, it's divided by the mass multiplied by the velocity. So it means that the heavier the object, the faster the object, the wave of your object is getting smaller and smaller. What does that mean? It means that if I take the mass of an electron, which is 10 to the minus 31 kg, okay, then, and I make it go at 1,000 kilometers per second, you know, in some experiments we have this is a typical number. So you'd see that the wavelength of your electron, so this wave, is going to be about 1 nanometer, right? So at the scale at the microscopic scale, it matters a lot, and that is why we'll see a lot of quantum behavior from the electron. On the other hand, if you apply this to a tennis ball, let's say a 50-gram tennis ball moving at 20 meters per second on a tennis court, you'll see that the tennis ball has a wavelength of 10 to the minus 35. Okay, that's like 20 orders of magnitude smaller than the atom. It's completely inexistent. It exists theoretically, but it has no impact at all on whatever. But theoretically, it exists. Any human being has a wavelength, theoretically. Okay, so microscopic behave only negligibly as a wave, completely negligibly, maybe even less than negligibly. So that's that, and there. So, but the point is, what is the meaning of this wave, right? So, okay, I'm telling you things have a wave nature, and for the electron, I didn't show you the experiment. We have similar experiments that show the interference pattern of the electrons. We have some in our lab over here. So someday you guys can actually see these interference patterns that we see for life with the electron. We have an electron gun. We can send those electrons in the lab over there, and there's some kind of diffraction grating that allows us to create this diffraction. So we can even show you that in the lab. But what is the meaning of this wave? Okay, so imagine I'm going to give you a thought experiment. Thought experiment is not something that we'll actually make in a lab, but we kind of imagine how the physics, the system would behave just by imagining it, right? So imagine that we have two boxes, and we have an electron that is both in both of these boxes. And by that I mean that there's a bit of wave in box 1 and a bit of wave in box 2. And here there's no wave outside. That's why I made it to 0, because the electron is not outside. So in a way, this means that the electron here is at the same time in box 1 and in box 2. Okay, it's a superposition of electron being in box 1 and box 2. And there's a key principle here. So, as opposed to the rigorous postulates that we saw, maybe those of you have seen with Nicolas' talk, last week. Here, I'm going to give you a little more hand-wavy idea of them, but it's the postulates of quantum mechanics that are behind. So the idea is that the wave nature is actually preserved as long as the box is closed and nobody looks inside. Okay, so if the box is closed, nobody looks inside, then this kind of superposition, this weird thing that is electron being in two boxes at the same time, this is preserved, right? But what happens if we look inside? And the whole interesting part is when we look inside, right? So let's look inside the box. What happens if we look inside the box? Any non-physicist? No? What happens if we look inside the box? So if we look inside the box, when the electron is observed, the electron becomes a particle. It's going to either materialize either in the first box or in the second box. Okay, there are two possible scenarios. Either the first scenario, electron appears in box 1, or the electron appears in box 2. So we have two different scenarios, but how do we know which of these scenarios happens? These are, if you do that experiment, this is what will happen. There'll be, sometimes you'll see it here and sometimes you'll see it there. This is what we call the collapse of the wave. It becomes a particle. Now, right. And basically, yeah, after sometimes it actually in the box, it will become a wave again. So what tells us whether it's scenario 1 or scenario 2 is going to be the wave amplitude squared. So we have a wave here, right? So the amplitude of that wave squared is what will give us the probability of finding that that electron either in box 1 or in box 2. Okay, so this is the wave. What's the amplitude? Amplitude is just basically, the height of this, and this is the height squared. Okay, so based on this, what is the most probable scenario? Finding the electron in box 1 or in box 2? Yeah, in box 1, right? Because it's actually, there's more wave, the wave has a higher amplitude over here, right? So that's basically how quantum mechanics work. With the highest wave, you get the highest wave amplitude. You basically get the highest probability of getting scenario 1, right? And, right. So the question we wanted to ask, and basically what I want to ask is, okay, I have an electron in a box. How can I make a qubit out of it, right? So can I make a qubit out of it? And to illustrate this, to understand that and to understand what can be a qubit, we have to make this a little bit more quantitative. So what I mean is, what exactly is the wave of that electron in the box? So to understand this, we can make an analogy with a rope. So suppose you have a rope and it's tied to on the two sides, right? You have two basically anchors, and the rope is tightly tied on both sides of two walls. Okay, so here you get different possible modes of oscillation of that rope, right? That's one possible mode of oscillation. The second mode of oscillation is going to be that mode, a little bit higher frequency. This is going to be an even higher frequency mode. Okay, these modes of oscillation of the rope are very special. These are self-sustaining modes. For mathematicians, these are normal modes, physicists, normal modes, right? These are normal modes, are self-sustaining in the sense that if you stop them, they'll stay in the same mode, right? You can also have superpositions of these waves, right? So I can add these three modes and I'll get something more complex, but I'll get something that doesn't look very self-sustaining. I'll get something that's sloshing up and down, slightly going right, going left, right? So these are not self-sustaining modes. These are additions of these three modes. Okay. So these are kind of special, and there's nothing in between, right? This is one oscillation, and there's no mode with an oscillation exactly in between those two. So these are kind of discrete states. What about the electron in the box? So the electron is actually similar in some sense because it's also as if tied, because there's two walls, and therefore the wave basically has to be zero at the wall exactly. And it turns out, practically, when I solve the quantum mechanical equations, which I'm not going to do here, I'm just going to show you, you'll get exactly the same mode. There's a direct analogy. So this almost, I'll specify what is not exactly analogous. And so these are the different modes. This is the lowest frequency mode. Oh, it says No, that's fine. So there's the lowest frequency mode, higher frequency mode, and even higher frequency mode. This is the fifth mode, and this is the second mode. I don't have any battery in my clicker left. I think it's going down. Yeah.
Before looking at the box picture in the waves were kind of like if you're finding the electron in that box.
Correct.
Now when I see the wave dipping down, I should not interpret it as negative probability.
No, because it's the modulus squared. You see, because it's a modulus squared, so that's the time evolution, right? So that's the wave, and it's going to evolve in time, and in fact, it is going to become negative from time to time. It's a modulus squared. In fact, the limit of my analogy is these modes are exactly identical. In fact, mathematically, this is a cos, and this is a cos. This is a sine, this is a sine. Exactly. Okay, this is this and this and this are sines. These are their cos, identical. But this has, especially when you evolve in time, you'll get a complex component. This is where the parallel between this and this field is like here you have an extra component which I haven't plotted, but there is a complex component, which also when you take a modulus squared, it doesn't matter. It will just add up to the amplitude. But the point is, yeah, so these are kind of the self-sustaining modes, right, of the box, of the electron.
By saying self-sustaining modes.
Yeah, so okay, so it's a loose way of saying things. For physicists, this is what we mean by normal modes or eigenstates for the electron in the box. So what I mean by this is a mode that if I start it, if I basically drive it at exactly its own frequency, it will remain the same mode. It's not going to become a different mode, right? So there's only one frequency inside, right? So if I can drive this at a single frequency and I'll always get the same mode. Here, there are different frequencies involved because all these modes have different frequencies. So if I drive, there's no way I can create that mode at a definite frequency. So this has a definite frequency. This has a definite frequency. This doesn't. This also has a definite frequency or definite energy, especially we're going to talk in quantum mechanics. Whereas superpositions of these are not going to have a definite energy. They're going to have an indefinite energy, which are not going to be associated, right? So these are important modes because if you start them, they remain in the same state. Whereas if you start in anything else, then the system won't stay in the same state. So you can't make a qubit out of it. Right? That's what I'm getting to. The point is you need a mode that stays the same if you want to be able to create a system in state 1 and leave it in state 1. It has to be an eigenstate. If you prepare, it has to be a self-sustaining mode or eigenstate, right? So the point, see, is, right, and so my point is now you want to make a qubit, theoretically, out of this electron, then you could define this as being my 0 state and this as being my 1 state quantum state. Okay, so this is, and basically I can also create a superposition. This is allowed, but what happens if I superpose both of these? Again, I'll get some kind of sloshing kind of mode, which is not really self-sustaining. It's self-sustaining, but after some time, and doesn't have a definite energy, right? It'll be like, sometimes it will be 0, sometimes it will be 1. It's actually oscillating between the 0 and the 1. It's not always staying the same. Right, so that's the idea of how we can make a qubit. Qubits are identified with with some of the self-sustaining modes of a quantum system, some of the eigenstates of a certain system. Let's say this is 0 state, this would be the 1 state, and then this is how you would want to encode your quantum information. Yeah.
What exactly are you defining as a qubit or what?
So here, a qubit it's kind of this abstract concept that basically includes both the 0 state and the 1 state, right? And you can either prepare your system and make it in this state or in this state. So that's how then you can encode information by either making your system in that state or in that state. I'll talk a little bit more about control, so it's going to be a bit more clear. Okay, this is just to give you a gist of how we are actually going to create these qubits. Now, the last point that I want to make is the Heisenberg uncertainty principle, quantum mechanically, and it basically tells you that the uncertainty of the position times the uncertainty of the speed, right, of any particle has to be greater or equal than a certain constant. Again, you can see your Planck's constant over here, and this is divided by the mass. Okay, what it tells you is that no object in the world can actually be completely located in space. there's always going to be a certain uncertainty in the position, depending on how, how big is the uncertainty of the speed, on the speed of your particle, of course. Okay, so there is a certain uncertainty on the position, and this is uncertainty on the position is what is going to force is going to make it create a lower limit for the size of objects, for example, the electron. Okay, and this lower limit on the position on this uncertainty is what defines the size of the electron state in, let's say, the hydrogen. So that is the lowest energy state of the hydrogen atom. This is an image created, from Nature in 2013. One of the first actual images of the atom of the electron. And so this width of the electron, okay, is actually given by what is the limit on this uncertainty. Okay, just the uncertainty principle won't give you the size. Okay, this size over here, but it will tell you. But what it tells you is that there is a limit, right? And this explains what is the size of the atom, right? So the red thing here is not the nucleus. Actually, this is all the atom. The nucleus is so small that you don't see it. But this actually explains this thing that we call the electron cloud. Basically, the electron is spread in space. Okay, it has an uncertainty delta x because of this uncertainty principle. It cannot be smaller than this, right? This is one way to understand why the electron has this large cloud instead of being just a point particle, let's say, on the nucleus. Okay, so it spreads, and it spreads just enough to satisfy the Heisenberg uncertainty principle. And right, in some sense, this is also why the electron cannot fall on the nucleus, right? Electron is minus and the nucleus is plus. Why does it not fall? Well, it's because of the uncertainty principle. The electron has a certain size and cannot be smaller than that. Okay, so this is the first, the ground state, but then the other S shells would be these ones. So this is the S2, I guess, S0, maybe S1, S2, S3. So these are the higher states of the hydrogen atom. And so this one we understood using the Heisenberg uncertainty principle. Now the higher states, these you can also understand using the concept of self-sustaining modes. So you'll have basically an electron is also going to be like confined just like in a box, but here it's confined because of the attraction of the nucleus. It's going to be confined. In this confinement, it is going to going to present some self-sustaining modes, which we call the eigenstate of the electron. And so these are the different states that you can see. There's nothing in between. These are discrete states again. Okay, and so this is what we can define as a qubit. Okay, this time it's a bit more concrete. With the electron in the box, that was just explaining how we can create a qubit. Now with the atom, we can actually use these two states and basically create a qubit out of it. Yeah, these are experiments. So they are measurements of the actual electron cloud. I don't.
Principal quantum number changes and then you get these images.
Yes. Yeah. Well, okay. So these are only the S shells, right? So then, especially in the first excited, you'd get the. But yeah, principal quantum number changes, right? Exactly.
Them to be not self-sustaining or
They're all self-sustaining here. I mean, they're all eigenstates. Sorry. Well, it's also self-sustaining. Sorry, that's true. But I want to emphasize the fact that this you can understand with Heisenberg uncertainty principle in a heuristic manner. Okay. And these, well, you cannot understand them with Heisenberg uncertainty principle, but using the concept of self-sustainability of eigenstates, you can get these extra states. Okay. That was kind of the point I was trying to make. Okay. Now we have an atom, but how do we control this atom? Right. So we need to, we want to do quantum computation. We will need to make one state is 0, we need to make it 1, or it's 1, we want to make it 0. So this is my 0 state, okay? So what happens is atoms can absorb photons, and if that photon has the exact right energy, right, then it can be absorbed by the atom and go to the first excited state. Okay, that's called photonic absorption. But an atom can also spontaneously emit. It actually always interacts with a neighboring field. And an atom that is in the excited state, in the 1 state, can always emit 1 photon, and that will downgrade it to the ground state. Okay, so it came from being in the 1 all the way back to 0. Okay, so this is one way you can manipulate your qubit, which we have defined as being this being my 0 state and this being my one state. Okay? Many things can be qubits. The key is how do you manipulate, right? So, and this is actually the first success actually manipulating this qubit, right? So the experiment works this way. So basically there are two mirrors that basically can focus light of a certain mode exactly between those two mirrors. So these are extremely high quality mirrors, okay? And they can actually keep photons for a certain amount of time bouncing between these two. Okay, so imagine you prepare your atom in your one state. Okay, so my S1 state, my excited atomic orbital of the hydrogen atom. And then I'm going to send that atom through the cavity. What's going to happen in the cavity is the atom is going to decay to its ground state and while emitting one photon, okay, and depending on how much time it's going to spend in that cavity, it can reabsorb that photon, go back to the excited state, go to the excited state, redecay. And so this process can happen multiple times, depending on how much time the atom actually spends in this cavity. Okay, it goes at about 350 meters per second, this atom, and the speed at which it goes will tell you how much it interacts in there. Okay, so at the end of its travels through a cavity, it will end up in a superposition of 0 and 1, right? Because it will have emitted a photon, and in general, it will end up in a superposition of these both these orbitals. Yeah.
What is the spatial side of this mirror? Like of the order
The spatial side of?
this setup, this mirror. Just order of magnitude.
Okay, so I would not know that. The only thing I know is that this is like a box. So the frequency of the wavelengths of that mode must correspond to the frequency of, it's about 50 gigahertz, the frequency of between these two shells, right? So it's actually rubidium atom. I'll mention that just after. So rubidium atom and the two shells we're considering are separated by h 50 gigahertz, which is basically the energy of the photons we need. So the size of this mirror would basically have exactly the size in order to have photons of that energy. Okay, so that's an experiment that was done in 1996. Okay, and basically this is what you get if you measure the probability of being in the excited states, how much we are in the one state as opposed to the zero state. And so you get this curve. So initially you are at 1, you are in the one state, right? Because we prepared it in the one state, remember here, so it was over here. And depending on how much time it spends, so we vary this with the velocity, it is going to oscillate between 1, 0, 1, 0, 1, 0. These are called Rabi oscillations. And kappa, basically there are some losses, right? It's a leaky system, and the losses are going to create, explain this decay over here. Yeah.
As you are increasing the interaction time, the time, like the probability of spending time is getting lesser. Why is that so?
So the slower it is, the interaction time is higher. Therefore, it is going to see if you just interact a little bit. If your atom is very fast, it's just going to be able to interact a little bit. So there's only a little bit of photon that's going to decay. Your atom is going to go from 1 to 0, but it's not going very far because it just whizzes through and there's not much interaction. If you spend more time in the cavity, what's going to happen is it's going to very slow. So there's a lot of time to interact. So your atom can emit its photon and then slowly reabsorb it, emit the photon, reabsorb it.
But reabsorbance doesn't take it to the previous.
No, because of the decay. So there are some losses, and that's the point. So this is the initial state, and then it will never go back exactly to that state because of the losses. At least in this, in this experiment, the first experiments, there are a lot of losses, and so this way. Now these days you can actually just have these oscillations going on forever.
That setup related?
Yeah, to let's say, the photon just imperfections on the mirror, especially, right? That photon is going to actually get absorbed at some point in the mirror. So a single photon, right, in the mirrors, they're pretty good, but they are single photon particles, so they actually in the end they do get absorbed by the mirrors.
How do you capture a single photon? How do you separate?
That's pretty difficult. So okay, so let me just get back to that to your question. I just want to mention. So this is actually these kind of experiment that led to the Nobel Prize 2012, right? For groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So it basically was a reward for actually managing to manipulate the systems, right? This is something that people had been trying for a very long time. So these are quite important experiments. So my point is also, so this was not done using hydrogen atom. As I told you, they were done with rubidium atoms, but it's exactly the same principle with different shells. Okay, it's possible with hydrogen atoms, but it's actually very hard to actually produce hydrogen atoms because you have to dissociate H2 atoms, and it's very hard to create a gas of them. Rubidium atoms, it's easier to ionize. So you can ionize a lot of rubidium atoms, and then I don't know exactly how they'll do, but they'll ionize these atoms, and then they'll have to collimate this. So you'll basically be getting a gas of those atoms that are moving in every direction, and they have some techniques to collimate them into a single, strain of atoms. And they kind of can, then they can adjust whatever parameters in the experiment to get one atom at a time. Okay, so this was done with rubidium atoms. So today, 20 years later, basically, more than that, 30 years later, basically people are actually now able to control them and levitate them in magnetic traps. So they can actually trap these atoms in lattices like this. Each of these dots is one atom. Okay, not a hydrogen atom, again, it would be a rubidium atom or cesium atom, some other kind of atom. And now that they have optical tweezers, they can actually micromanage all these atoms in there. Okay, that's a very relatively recent experiment, and they make quantum computers out of these. So this is one of the contenders for quantum computing are these atoms, neutral atoms. Now, one of the main issues, for those who know, these are 2-qubit gates that are a bit slow. But see, the main point here is that these are very delicate setups, and the technology is not mainstream, right? So the question is, can we make better atoms? Can we make actually atoms with, that use the technology that we have today, foundries, chip making, and everything? Can we make something on chip that would be a qubit? That's my question. Yeah.
What is this slow thing in the physically, like slow means what? Like,
Slow, which slow? Oh, slow here, okay. See, because basically when they have the optical tweezers, and let's say this is a 0 and this is a 1, they'll bring these two atoms together close by, and they have a way, and once they're close by, they have a way of making them interact and create a swap gate to swap it. But that interaction, basically, the swapping of quantum information is very slow as compared to other contenders for quantum computing.
information remains long in one of those states.
No, it's just the swapping. It's just the information is there. Is that it will take like too long. It will take too long to actually. Yeah, exactly. That would be 0 and there 1. You just want to swap that 1. You want to swap it in this qubit. So it becomes like this. What you want is this. You just want to bring them together. You need speed for quantum computing. It's a computation, right? And one of the things is you need to be able to swap information between qubits a bit faster. Okay, so yeah.
You're talking about swapping.
Oh yeah, this is like a swap gate. I'm not giving details, but yes.
Are the atoms being swapped, or is the one which is up going down and the one down?
Yeah, one is so that's the first qubit. This is the second qubit. So the first one is going to 1, and the second qubit is going to 0.
So your atoms are frozen in space. It's just that you're changing the state.
Yeah, that for instance, not really. Actually, use the optical tweezers. You move whenever you want to do a gate. You have to bring them together into some location. They'll interact, and then you bring them back. The optical tweezers are they actually, that's how they do it. States will interchange in this case. Yeah. Okay. So we want a different kind of qubit. Now, before telling you exactly what the qubit is, question is, what kind of system, what do we need to make a qubit? So can a harmonic oscillator be a qubit? Why a harmonic oscillator? Because it's the most ubiquitous kind of system, in the universe, mostly, or one could say. And what's a harmonic oscillator? Is like a mass on a spring. Okay, so the question is, I have a mass on the spring, and let's say I want to use this for a qubit. Okay, now what is going to be the lowest possible state? Let's say the ground state that we want to use for our 0 state for the qubit. What is going to be the lowest vibration state? So quantum mechanics tells us, again, that there's an uncertainty principle, right? So what's going to happen is, instead of having a well-localized mass, I'm going to get a delocalized wave packet in this way. Okay, so I'm basically going to have a wave that is going to have a spread that's basically going to agree with the uncertainty principle. So again, I have an oscillator, but instead of oscillating, it's a bit everywhere between these two things, right? Here is the same, these are basically the edges. So the oscillator, basically what it means is it can never be static. It can never be static because of the uncertainty principle. It always, even its lower state, will have a certain spread. It will always be oscillating a little, right? And this is why, for example, there is no such thing as an absolute zero of vibrations, right? What is temperature? Temperature is vibration of matter. So matter can never stop vibrating because of the uncertainty principle, because oscillators, always vibrate. Okay, anyway, so this is a slight digression, but the point is my harmonic oscillator at its lowest state is going to be a little wave packet, and similar to the electron in the box. And the higher states are going to be these self-sustaining states. Again, so they're going to be, because the oscillator is a bit like it's confined by the spring, right? So for the electron in the box, we had walls, so we had a confinement. Now we still have a confinement. We have this spring that is not allowing the mass to go too far away, right? And so these basically modes, they look very much like the modes in the electron in the box, where you have a confinement, right? You have basically these waves that are quite discrete. And these, I haven't made the videos, but they would oscillate in the same way if you wait for some time. Okay, so, and if you go even further, you can look, you have an infinite number of these states. This would be like the higher states. And so these are the self-sustaining states. So the first one, we can understand it with Heisenberg uncertainty principle. The wave is spread. The oscillator is basically delocalized. The system is delocalized because of our need for uncertainty. And the higher states, again, like these self-sustaining modes. Here, I'm just giving them to you. And, for the higher states, for the 10th state, these is still going to correspond to the extent of the oscillation. You can still imagine that oscillator oscillating between these two extremes over here, except that now our oscillator is actually a little bit everywhere in between these two extremes of oscillations, right? And here you'll find our de Broglie wavelength. So this wave here is going to be given by h divided by mv. And so you can see that velocity, because our oscillator is moving very fast over here in the middle, there's actually a smaller wavelength over here because it's moving fast, and it's actually stopping at the edges. When it stops at the edges, it has a small velocity, so you can see that the wavelength is actually getting bigger. Okay, anyways, the point is we have these states, and we could make a qubit out of it in this way. We could just take our first state and our first self-sustaining state and say, okay, let's encode information in this. And so these are basically, different frequencies, different energies. The more oscillations you find, the more energy you have. So the first state, has E0 energy, then E1, E2, E3, and this creates a ladder of quantized levels. Okay, so these are basically the energies of my quantum states. Okay, but the problem with the mechanical oscillator is what? The mechanical oscillator, the problem is that there is damping. You've all seen that a mass on the spring, eventually the spring is going to start dissipating and is going to relax to its own, because of friction inside the spring, it's going to stop and eventually, slow down to zero. Okay, so that's the main problem. Mechanical waves dissipate very fast. But there's another harmonic oscillator, and this is kind of one of the key points of what I wanted to emphasize today, is that the electric circuit, the most simple electric circuit, the LC circuit, is also a harmonic oscillator, exactly in the same way as the mass on the spring. Okay, what do I mean by this? So the mass on the spring, it's oscillating this way. If I look at the position, right, it's going to move like this, like a sinusoid, as a function of time, right? That makes sense. Basically, you start from here, and it's moving as a sinusoid like this, right? So in the same way, this is my function, which represents the position. And the momentum is basically just another curve. It doesn't matter. But the position is moving like this, right? What we have seen so far in the previous slide is then the quantum mechanically, we have eigenstate, we have self-sustaining states, and these can be my 0 and 1 qubit states. For an electric circuit, so what do I mean by an LC circuit? I have a capacitance. I have a coil over here. It's an LC circuit, okay? So what happens is when it oscillates, you have a current that is going to oscillate slosh back and forth like this. Okay, and the very fundamental point here is that actually this sloshing of the electrical current, this oscillation of the electric current, behaves exactly in the same way as a mechanical harmonic oscillator. Okay, what it means is that if you look at the current, it's going to oscillate negative, positive, negative, positive with the same mathematical function. And because of that, I can say that basically an LC circuit is identically theoretically to that, right? And what it means is the eigenstates, I mean the self-sustaining states, are going to be the same thing as what I had for the mechanical harmonic oscillators. Okay, so you'll tell me what I'm saying is that I want to use an LC circuit because they don't dissipate. Right? And yes, mass, if friction in a spring will dissipate. But electric circuits also dissipate. They also have resistance. So why would that be any better to use an LC circuit than a mass on a spring? Because anyways, they also dissipate. But that's not the whole story. Yeah, right, exactly. Within the resistance, this is an ideal one, but if you have a resistance, it would just decay. The oscillation would get lost, right? The one state is oscillating faster than the zero state, so it just decays. The solution is superconductivity. So if you use superconducting circuits, meaning you go to a low enough temperature with aluminum, there are states of matter which are quantum mechanical, not going to explain, where basically you have no resistance. So my keyword here is superconductivity, means that there's no resistance if you got low enough temperature. So what's that? So basically, how do we build them? We'd build like an aluminum circuit. So this is how a chip would look like. You'd have an aluminum circuit, then you'd have some silicon chip. On the bottom, you would have some gold plating. Okay, so this is how a superconducting circuit chip looks like, and that's how you could build an LC circuit. So we use frequencies of about 5 gigahertz, so this is microwave range. Okay, and you have basically the reason we need to cool down is because we need the temperature, the vibration, the phonons, right? The energy of those vibrations to be much smaller than the energy of the excitations of my circuit. So my circuit is an LC circuit, okay? For those who have done a bit of physics, electricity, and everything, the frequency would be 1/square root of LC. That would be the frequency, right? So the energy of my quanta, okay, the energy of my excitations here are going to be h mu. So basically, the temperature has to be much smaller than my excitations in my circuit. Okay, just the bottom line is we need to cool down very low, and we need to cool down to 250, lower than 250 millikelvins. In practice, we cool down to 20 millikelvins. Okay, so 20 millikelvins above the absolute zero, that's how far we need to cool it down in order to be able to control these quanta in this circuit. Yes?
So why is current here behaving like a quantum system?
Say
Why is the current behaving like a quantum system in one of the
why is it behaving like a quantum system? Well, everything is quantized. So, the point is, because of superconductivity, there's no friction. So even though there are many electrons, these are like, collective oscillation modes of your current in the circuits that now play the role of the excitations. Before, I was talking about the mass. So that's why I tried the analogy, because it's a bit hard to picture with the LC circuit. The mass is oscillating. These are my quantas of oscillation. Here, my quantas of oscillations are we call plasmons. Basically, these collective oscillations of electrons, which is basically current oscillating. See, yeah.
Is something to do with the size of those channels? Because
it has nothing to do with the size. It can be big, actually. It doesn't matter. These are actually macroscopic systems from a quantum perspective. And that's what makes them very, very unique also in quantum science. So they're actually very big systems. Still, we can manage to control them quantum mechanically. Something very impressive. And before, in 1995, we thought only atoms were difficult. 20 years later, we can control like billions of atoms at the same time, because when we consider these quanta, it's like billions of atoms oscillating around that circuit. Billions of electrons, sorry. Yeah.
Unless this LNC can't be reduced so much further lower, so that you can have a reasonably high nu, where you can operate a bit of higher temperature. Because 250 millikelvin, like, you have to maintain that. That's an issue. So, is it possible to play with your LC to manage it? make it operationally bit more high temperature?
Too high, then basically at microwave frequencies, I didn't specify this, but you'll get too many losses, especially in the cables, and the dielectric losses as they start to increase. So too high frequency doesn't work, really. You'll get much more. So really, there's a sweet spot at this frequency. Too low is going to be a problem because of thermal vibrations. And as you say, we can't go infinitely low. But too high, then we get too many losses. So we don't want to go too high. Dielectric losses, especially in the circuits. There's an optimum, yeah, around this 5,129. This is basically what we play with. Yeah.
The inductor create a magnetic field which could interact with things outside that could lead to loss.
That's a huge problem we have basically in supersonic circuits, is that there are these fields. You're completely right. They're actually not localized as circuits that create big fields. And when you want to create multi-qubits on the same chip, they interact with the other qubits. And that's why you have to space them, and that creates that demands a lot of space. So yeah, you're completely right. You have to be very careful. What you do is you create different qubits with different frequencies so they don't interact too much with one another. Okay, so basically what if we drive, so we have this LC circuit, okay. Now what happens when we drive that qubits? Okay, so I have my different levels. I've chosen my lower level to be 0, my first level to be 1, and then these are the higher levels. I told you there's an infinite levels of the number of those levels. And now I'm going to drive that system. I'm going to send like a lot of photons at a certain frequency just to drive it. And you see, we're going to have a problem here. I'm sending one photon that allows me to create a transition from 0 to 1. But another photon, and this is a classical, I'm sending like classical microwaves, okay? So there are a lot of photons. That's why I'm drawing many photons and not a single photons. We don't know how to create single photons. I mean, we know, but it's very hard. And so generally we just send lots of photons. So now take another of those photons with the same energy. And because it's the same spacing, what happens is my state, another photon can bring this state to the second state. And this is a big issue because see, what we have happened is we have exited the 0-1 subspace. Suddenly we were in the 0 state and we ended up in a state that's actually a superposition of many, many states. But only these two is our qubit. Our information, as long as it's encoded in there, it's properly encoded. Whatever goes outside is lost. Okay. So the problem here is we have equally spaced energy levels. The qubit spreads to all levels when we try to excite the first excited state. And this is why this cannot be a qubit. Okay. So we have to find some other problem. The problem is the linearity of this harmonic oscillator. Basically, it's a linear force, and it has basically equally spaced levels, right? H mu is basically the energy between two levels, where mu is the frequency of my oscillator. Instead, what we have to do is kind of break this equality of the levels. So to do that, we actually have to add some nonlinearity to the levels. What we do is we use something that has a nonlinear force. And for physics students, you would know that the first nonlinear system you learn about most often is basically the pendulum, right? So this system is a pendulum, and it has a different dynamical behaviors compared to the harmonic oscillator, right? And so this pendulum is actually going to have, when you look at the quantum levels, you'll see that its levels are actually not equally spaced. These levels are spaced like this, and the second excited state is slightly, the difference is actually going to be lower than, they're not equally spaced. What it means, yeah, exactly. So now this is different. So this is, again, I'm coming back to my mechanical analogy, but with a circuit. How do I include a nonlinearity with a circuit? I have a mechanical pendulum, that's fine. We know that's nonlinear. Electrically, we need something a little bit more complex. And when the device we use is called the Josephson junction. Okay, so this is a superconducting device. I'm not going to go into the detail of physics. There's a lot of physics basically on the Josephson junction. Basically, the Josephson junction is basically a superconductor, then an insulator, and then a superconductor. It's basically a tunnel junction, and that is going to lead to a nonlinear inductance. So the symbol of this junction is given by this. Okay, so you might see it. And the key point is that the inductance is nonlinear. What it means for physics students is that basically the flux is not a linear function of I, of the current, right? Instead, you have a complicated function, right? Some function, and it's a complicated function of I, and because of that, this actually can allow us to create a proper. Sorry? LJ is the, okay, inductance of the Josephson junction. I called it LJ. This is a Josephson junction, so this becomes LJ. Yeah, I didn't specify that.
But this in turn makes the distances different.
Exactly. So the distances over here, it will have exactly the same effect as a pendulum. Exactly. That means if you even look at the Hamiltonians for the physicists, they'll be identical. The pendulum and the Josephson junction plus a capacitor, exact. What it means as physically, they're exactly the same systems. It's a bit hard to understand. I mean, I'm making an analogy, but physically it's very deep. This idea that the mechanical oscillator and the circuit oscillators are identical from a theoretical point of view. That's why, yeah. So what happens here now, you see, is now I can again, instead of my linear inductance, I've added my Josephson junction. What happens now is I can send photons, and what happens is, okay, one photon has created a transition from this state from 0 to 1. That's great. I've gone from 0 to 1. I might want to do this transition in my quantum computation. But now I'm not allowed, with the same energy, I will not be allowed to go to the second state. So what will happen is I send another photon, and that goes back to 0. Okay, so I can do that as long as I'm putting photons. This is going to oscillate between 0 and 1. In other words, I've started in 0, and whatever I get later is going to be 0 plus 1. So I have created a qubit. Finally, I have a qubit, something that actually behaves like a qubit. And why do I call this an artificial atom? Because it has levels like an atom that are not equally spaced. That's a key point. And I can basically excite those levels using photons. These are not going to be optical photons, they're going to be microwave photons. Nevertheless, they are photons. Electrical signals, so there's some electrons playing a role, but still, yeah.
That's a capacitor.
Correct, that's a capacitor.
So as the capacitor discharges, can it not, at some point, if you're not supplying it with photons, as the capacitor discharges, can you not have almost a simulation of it going from energy for it to go from E1 to E2?
But E1 and E2 are, properties of the whole system, of the whole circuit, not just the capacitor itself.
Yeah.
Right? So when it discharges, you're right, it always discharges because this is an oscillation. So it actually oscillates from charge being on the capacitor to going on the other side of the capacitor. There are two ways to see it. Either it's the charge on the capacitor that oscillates, right, between these two, or it's the current that oscillates between like this being positive or negative.
Oh wait, that doesn't change it because it's a superconductor still.
Right.
So it's not going to blow in its time or anything.
So exactly, that's the point. There's no actually resistance, and that is why you can, this is the key. The superconductivity, no resistance, no dissipation. That's why we can keep those systems continuing in this oscillation for very, very, very long. Right? They can oscillate without dissipating. That's why we can manage to create qubits out of it and control the quantum information. Okay, this is see, the point is I'm going to need to, when I'm sending those photons, I'm sending them through a cable, right? So I need a port. I need to port, so it's going to be a circuit, so I need to kind of add a port on my circuit in order to excite it. So I'm going to send this through what we call coaxial cables. Coaxial cables can propagate microwave frequencies. So then my microwaves, my photons, they're being sent through that. That's why I symbolize this with an extra port. They're not photons sent in vacuum. See, it's not like I'm sending photons in vacuum, right? I'm going to connect the port. I'm going to collect a coaxial line and send those photons in this way. So it's still a circuit. Even though I call them photons, still a circuit. These are like photonic circuit, electronic photons instead of, photons in vacuum.
How small have we currently gotten this setup to?
This, okay, very good. I'm getting that. Good. So this is an actual experiment. So this is basically a dilution fridge, about 1.5 meters. Okay, basically what happens is you need different stages to cool this down. So you start at 4K, then you end up at 1K, then 100 millik, and then finally you get at 20 millikelvin on the bottom. So it's always at the bottom here that you'll actually put your samples and everything. Okay, and so the chip is going to be there. So this is actually the sample holder, and the sample holder is about 1 centimeter, 2 centimeters. And the chip is the small black thing that you see here. That's the chip. It's 5 millimeters times 5 millimeter. If you zoom in again, so that's an experiment from very recent 2023 experiment. That's an actual image of the chip. It has false colors. That's why it looks like a very nice candy color image. But it's actually this is actually the image of the chip that they use for the experiment. Okay, and the qubits are these structures over here. So they're basically what you see, these structures is mostly the extent of the structure to create a capacitor. Basically between here and here, you'll get metal, aluminum. So they're going to be capacitor because you have different plates that are close together. So these 4 things are actually the qubits. This is a 4-qubit chip. We're not planning to scale here. That's actually a fundamental. Yeah, I'll tell you exactly what we're trying to do here at this point. This is a 4. Yeah. So these are the 4 qubits. So I'm just giving you an image. There'll be a Josephson junction, but this is 0.2 millimeters. Okay, the size of that. In the junction, you cannot even see it. It's nanometer sizes over here. But today's nanotechnology facilities, they allow you to build this with very high precision. So even those junctions you can. But the tricky thing is always creating those very, very small junctions that are here at the edge. No, so these are couplers. Couplers, because when you actually, for separating qubits, one way to actually exchange the quantum information, you need a coupler. You cannot just put them together. Otherwise, they would just always exchange information. You want to programmatically exchange information, 1 into 0, 0 into 1. For that, you need an actual coupler that can be made on and off.
So basically, couplers used to translate between Q and Q. So C13 is between Q1 and Q3.
Exactly. So basically, you have couplers between each of them. This is a different one. The C12 is a different one. That is a different thing. But these 2 are there, yes, to swap between this and this between this and this. Correct. I'm going to talk about this a little bit more as.
How do you read the information of the qubit though? Because you said you have a port for how do you actually ascertain this information?
Ascertain that it's 1 and 0. That's a very good question. The point.
System.
Yeah. So no, that's a very good question. You have to connect it to a resonator. And when you couple your resonator to your qubit, depending on 0 or 1, it's going to have a small effect on your resonator. By a resonator, I mean an LC circuit. So you'll bring an LC circuit close by, so you'll have to fabricate that. And that qubit is going to change the frequency of your resonator very slightly, depending on what state it is. With that, so then you measure the state of your resonator, and that allows you to measure the state of the qubit.
Is the resonator on the qubit holder?
No, it will be on the qubit holder, but here actually we cannot see it. They might, I do not know where they have put the readout mechanisms.
But doesn't that become an issue because immediately then you'll have some sort of energy dissipation from the.
Yes, no, you're right. That also, the moment you add a resonator, that will actually create some dissipation. And these are things you have to minimize as much as possible to actually, but you're right. Any other structure or whatever things you add, and you do have for each qubit you want to measure, you will need that.
So they wanted didn't connect 1 and 4 here. Is there any reason why 1 and 4 are connected?
1 and 4, because okay, so I'm going to get to that point. Okay, so give me 2 minutes. Let's see if I, right. So, okay, so basically, I'm going to go back to the chip, okay, just in a few slides. So I'm almost done, only 5 more slides. So basically, so this is an IBM chip. So IBM is one of the big contenders in separating qubits, right? Google and IBM. So we don't know exactly what is in their chips, but for a recent chip is that this Heron chip that has 133 qubits on the same chip. So these chips are a bit bigger than the ones you find in experimental labs, just because they have to put more qubits on them, so they're like 20 millimeters. And you have 133 superconducting qubits. We know what they look like though, right? I mean, we know that you're using the Josephson junction plus capacitors, so this whole thing inside, but the exact design we don't know exactly. But the problem is the same for everybody trying. One of the big problems for everybody in superconducting qubits is for each qubit, you need one control line. Because you need to be able to control each qubit individually, right? One line, if you're connecting the one line to all the qubits, then all of them are going to change simultaneously, right? So here, and these are all the control lines, these ports and these lines that you have to put inside. And you can see how fast this is going to scale. The number of lines, so the parameter is going to scale much slower than the area inside. So there's a limited amount of qubits that you can stack inside in the area, because eventually on the perimeter you won't have enough space to actually put the to plug in the wires, right?
I don't think you will the bottom phase.
Yeah, so there are different ways to actually. So this is a 2D architecture. There are 3D kind of hybrid architectures, but they are not necessarily much better. IBM doesn't use that. And there are limitations there also, even in the geometry. insane. You might gain a factor of 2 or 3, but you won't gain much more.
Would it be more difficult to cool the more 3D of them?
No, not necessarily, but it will be bigger, harder to cool if you have to make your sample bigger and bigger, because then you need a bigger and bigger fridge. Yeah. No, cooling down is a big problem. That's why we can also not, extend the chips to be too big. So, each qubit needs a control line, and you need to find a solution to scaling up, to making more and more qubits, right? So IBM, basically has this, this roadmap, and they have created, for example, what their solution is. You get a chip. Let's say you have 133 chips over here. And what you're going to create, you're going to get interconnects between the chips. So you get the wire that's going to connect these chips. And they have a connection between each chip, 2 and 3, 2 and 1, 1 and 3. Okay. But eventually, when you go to thousands of qubits, millions of qubits, right, this is not going to work. You're going to need to get, if you have coupling each qubit with a different line to each other, it's going to be very difficult. What you will need is to actually couple. Let's say I have 3 chips with many qubits on each, okay? What I'm going to need to do in order to connect these chips, because they're too big, I cannot add more qubits on them, is, create some kind of waveguide. I'm going to have to connect them. So imagine this will be one line, this one wire, or what you can call it a waveguide, that connects all these chips. And what I want to do is send this information, 0 plus 1, let's say, to chip 3, that is in 0. Let's suppose it's in 0, the 0 plus 1, 0. And I want to send that information to a qubit here. So how am I going to do that? And one big issue over here is, one of the very basic properties of waves. Imagine, how do I transfer? Right. So imagine I have an oscillator. Okay, again, an oscillator on a spring, and this is water. Now, as my oscillator, it decays, okay, it's going to send its excitation to the water as a wave, right? You can see initially it oscillates, then dissipates, and that information. So the analogy with my qubit is that my qubit is oscillating, right? Remember, this is an oscillator, nonlinear oscillator, so it has an oscillation. Just like this mechanical oscillator. And it's going to send these, basically, its quantum information in a wave along that waveguide in exactly the same way, in a very similar wave profile as this. Okay, so it's sending it in both directions. Problem is, this is a property of wave. It sends the wave is going to propagate in every direction. There is no way I can actually send it right and not left if I'm just using a single qubit. It's a property of the emission of waves. Okay, so the way you send a stone in the water creates ripples in every direction, not just in one direction. So what do we do about that? Well, one way to go about it is, how do I send a photon, but in a specific direction? And one way to do it is the following. Instead of 1 qubit, I'm going to add 2 qubits. And I'm going to couple them, add a coupler between them so that I can start swapping the information between them. So I can send 1 photon, or many photons, whatever, and bring it to the 1 state. That's what I showed you before with these little photons and the energy state. So I'm bringing this to the 1 state like this. Now I'm going to activate the coupler. By activating the coupler, I'm going to create a swap between these two. But because it's swapping, actually I end up in a weird kind of state where none of these two are actually definable individually. Suddenly, the quantum state becomes entangled because you have 1, 0 plus 0. And what happened is I kind of transferred half of the qubit. So half of its state, half of it is in the other qubit. And it's 1 over square root of 2, right? So that's just basically a prefactor just to normalize. Doesn't matter. But you see that I still have 1, 0 and 0, 1. So if I had sent a little bit more photons, I could have transferred it completely. But because I stop in between, I created a system that is 1, 0 plus 0, 1, which is entangled. Okay?
This entanglement still can do with coupler.
Sorry?
This entanglement still happen to come with coupler.
Because the coupler transferred. So I start here, right? 1, 0. These are, and they're individual, they're not entangled. This is 1 and 0. And then I'm coupling them. So basically, I'm activating the coupling between them. So I start transferring one qubit, one excitation from one qubit to the other. But I'm not doing fully. That's why I get one. I cannot define each individual state. That's quantum mechanics. It's entangled. So it doesn't mean anything to say what is this and what is this. I can say what is the whole. It's an entangled state.
What would it fully look like? It become again another high sending another product.
Say again.
Do it fully.
Oh, if I can do it fully, yes, I have to basically activate the coupler for longer. I have to activate the coupler for longer, right? And then I will create a full Rabi oscillation, cool oscillation that will actually bring it to the back or all the way to one.
We get a product state.
And then okay, if you wait for long enough, you'll get back to a product state. You're completely right. So in this, actually, so this is basically a proposal that we came up with with my Japanese colleagues at the University of Tokyo, basically to create directionality. So I'm changing the symbols a little bit because this is basically the image from the paper. But you see, this is our first qubit, this is the second qubit, and we're coupling them at a certain distance on the same waveguide. And what happens actually when you send that entangled state and the emission, it has actually this state, this 0, 1 plus 1, 0. There's an additional phase you need to add. Okay, what's going to happen is this simultaneous emission through these two qubits is going to lead to a constructive interference on one side of the two qubits. So what's happening is they both have a little bit of one, okay? And so they're both going to be emitting their qubit simultaneously, okay? 0, 1 plus 1, 0. And what's going to happen is because of the extra delay, so this is lambda over 4, this is basically chosen very exactly so that the wave emitted from these two qubits simultaneously, they constructively interfere on that side, and they completely destructively interfere on that side. Right? So, yeah. So this is what happens. I mean, we can discuss a little bit more in detail about the exact physics, but basically, you can imagine there are two waves. Now, I've told you, how this quantum information is basically emitted as a wave. So there are two waves simultaneously being emitted because the qubit is simultaneously in the one qubit, in the right qubit, and in the left qubit. Right? The excitation is simultaneously in the right qubit, in the left qubit, and therefore there's a simultaneous emission, and these two waves are just going to, interfere. And this interference is what is going to give directionality. So what we have engineered in some way, my proposal is to create a chiral object, a device. But that object cannot be a single qubit. It has to be two qubits. Two qubits together coupled, creating that specific state, and that will lead to a directional emission. So now we can actually finally, thanks to this device, we can emit direct quantum information in a specific direction in a quantum network.
So can we say this is a process of creating, like we say when we had a coupler?
Yeah.
In real optical world, we use something called SPDC, spontaneous parametric conversion.
Yeah.
Instead here, if we use coupler, we create entanglement. That's what you're telling.
Yeah. SPDC is to convert.
Photon into entangled state. That's the process we use.
Yeah. Okay.
Is the coupler doing same job in the superconducting? That's my question.
I think so, because you're going from 1 to 0 also. So it's exactly equivalent. I mean, it is a different, you have many ways of treating this coupling. This is only one way, by the way, when we're separating qubits. There are other ways. Sometimes you can make this qubit tunable. You have different, okay, you can tune the frequency, okay. But yeah, I mean, I think it's exactly the same thing. If you're creating entanglement using that, I'm not so familiar with SPDC, so I'm not sure.
But what you have done is your proposal is that you're going to create one way it's constructing and one way.
Yes,
That's
yes.
the direction.
Well, exactly. And then actually, this depends on this phase. So how you create this phase, this you can do experimentally, just the technical aspect. And you can, because I told you that there's a quantum aspect involved in the states of quantum mechanics. So this is a quantum phase, an additional complex phase that you add. And if you have a minus I pi over 2, depending on how you prepare it, you can send it in the other direction, right? So if you just say put a minus sign over here, you can just send a wave in the other direction.
It's easy. It's a phase gate is easy. It's a single qubit gate. You can easily do it.
Yeah, it's not very complicated. The gate thing is actually very simple. That's not something that you can experimentally do. It's very hard. Finding a
Finding a superconducting coupler, then will work here will also be, I'm guessing that's the challenge, right? Trying to suit the chiral counters.
So this is there's no chiral, this is the chiral device, right? So it actually sends it right or left. It's basically, it's a device that is, direction dependent. So it's not a chiral coupler, it's a chiral device. It's basically dependent on direction. Okay. So basically, these guys have actually realized it. So that's actually the chip I was showing you. And you have 2 qubits, and this thing here is, so these are actually, what happens is, this is a detail of the experimental realization, but you need to add, there's actually, the waveguide has this weird property that is going, if you put 2 qubits connected to the same waveguide, they're going to start interacting. There's a swap gate that is going to start appearing. It's mediated by virtual photons. It basically, this is going to make it necessary for you to cancel that interaction in the waveguide using this. Anyway, this is a small technical detail. And so here is basically my 2 qubits, okay, Q1 and Q2, which I was showing you. We are preparing in this entangled state. And here I have 2 resonators. Okay, this is basically because we want we don't always want the, okay, one second. And this is the waveguide. So it's actually, basically the chip is small, right? And the wavelength of microwaves is pretty large. So in order to get the right separation between these 2 qubits, you actually need to weave that waveguide like this. So it's the same waveguide. And basically these 2 qubits, you have couplers here. So you can basically transfer the excitation to these 2 qubits, all the qubits, or resonator depends on, but here there are qubits. And this will actually allow you to create an interference between the emission from this point and this point into this waveguide. Okay, so this basically, and this is what they've managed to do. What they show is they've managed to get 96% directional emission on the right and 95% directional emission to the left. And okay, so with this device, they were able to actually get the directional emission. And I think this is my final slide. So the point is now what they did afterwards, and this is actually more, I forgot to put the actual paper date, but this is a paper from beginning of this year. So they've actually put 2, before there was 2023. Now this year what they've done is they've put 2 chips, one to the other, and now they were able to basically emit 1 photon here, send it in a 6 centimeter line, and reabsorb their photon in a different chip. That's what I do here. You can see this is my first chip, this is my first sample holder with my chip. It's connected by a line, and then you have another sample holder with another small chip. So they create this here, send it there, and reabsorb it here. In fact, they were able to create entanglement with this also. So from chip 1 to chip 2, because now we have, so again, these are qubits, but they're not the main qubits, okay? They are meant for emissions. So just forget they're a bit here for technical reasons. My main qubits are this: Q, Q3, Q4, Q7, Q8. And these 4 qubits, they were able to entangle them using this thing. So this is one of the ways they were actually able to send information and entangle 2 chips that were located on different, not in different fridges, and still in the same fridge, but now people can think of actually putting these chips in different fridges.
The entangling more chips, number of like possible states increases not linearly, right? Goes exponentially. So the computing power should increase as you add more chips. It shouldn't increase linearly. It should increase exponentially.
The computing power
of these chips as you add more of these modules together. The the number of possible states shouldn't increase linearly, right? It will increase exponentially. So
it will increase exponentially as the number of possible states that you can create by putting more and more qubits.
So if we can control that, so our computing power should increase exponentially. Right?
Correct. Then if you can actually create more and more, but that's quite futuristic. At this point, we're not very close to that. I mean, this is only one of the challenges. One of the big challenges is scaling, and that's one of the things that's why I'm discussing this, the parameter versus area problem. But in terms of coherence times, maintaining the quantum information, and all the other issues, I mean, there are so many more issues also than that. Decoherence is one of the main things. Yeah, the coherence is still correcting the errors that you get from current. You're right. That's one of the main things.
Also, clear that we can't generate all states.
Say again?
So we can't generate all states with all the two modules.
We are creating states in each module and then coupling them on the module level.
So we're creating a state on one of the chips module. You mean chip is module, right? On one of them, and then you can basically send some quantum information from one to the other. Now, if again you're sending just half excitation, it will create that will create entanglement, because if you send half of the information, you absorb half of it. What it means is you enter an entangled state in a similar way to. I don't know about that. That depends how you create your.
Obviously, if there are local unitaries that are acting on the module level, and the big unitary is composed of these local ones, so that cannot generate all. It can't scan the entire
I think in general you might be able to create whatever you want as in terms of quantum states. I think you could create anything you.
Because then we used those couplers to couple two systems. So at some point we will reach a level where we have, say,
Yeah. Okay. So here. Yeah. No. Here basically it's true that in this particular setup you won't be able to create any kind of state of these 4 qubits, right? But you might be able to consider this as 1 qubit, for example, and encode like your quantum information in there. And if you consider that as 1 unit, you can send that information here. But yeah, the problem here is you need directionality. You need to create a specific state that allows you to directionally send information. So that will constrain whatever you can encode.
Eventually, I was on the argument that at some point we'll have a chip of a certain size, say 100 qubit.
Okay.
And then there will be an array of these other qubits.
Okay. Yep.
And then all the states that we generate with 1,000 and then 1,000, then 1,000, and then you will take the tensor product or the unit formation of that.
Right.
This can't explore the entire space of all the.
Okay. Maybe.
Because if obvious, I think there are local units acting on individual ones.
Yeah.
And then you are coupling local units.
Yeah. No, but then no. I think if you properly couple all the chips together, there will be one way to engineer an interaction. So you can always send your quantum information to the other chip, and then within the chip you'll have a lot of complicated couplers again that are going to couple all the qubits. I think eventually you can create whatever state you want. But I mean, we can discuss this a bit more. Like maybe it's slightly more. Anyways, that's mostly what I had. So just to summarize the talk, we discussed what is an artificial atom. So basically, it's something that has like quantum levels similar to an atom that are not equally spaced, right? And we can use photons. We can access them using individual photons or drives. So we saw that one such system that it works perfectly is the pendulum, right? It has unevenly spaced quantum levels in its energy spectrum, and we can excite it using photons. We send like light to it, microwave light to it, and we can excite it from the 0 to 1 and 1 to 0, and it will always stay between 0 and 1. So this is what I mean by an artificial atom. It's a superconducting qubit made from this device that we saw. It's a Josephson junction and a capacitor. And its physics, its dynamics is identical to that of a pendulum, and that is why I brought you through the analogy, through the way of the analogy to actually to introduce this superconducting circuit. Okay, so then I discussed a little bit about the quantum, what people call these days interconnects, and one of the ways that was done recently was to use 2 qubits in this way using a coupler and to create an entangled state, and that entangled state allowed us to create directional emission. And because we have directional emission, we can now route quantum information on a 1D network, right? So yeah, that's it for the talk. Thank you. Any further questions?
We have time to give some idea of why still the patterns are. So I mean, how are the nodes in the superconducting? Like, how do a bunch of electrons start to behave like one system such that we can treat them as a quantum system.
How do they start to behave like this?
Basically, I'm asking about the super.
Yeah.
Scale.
So if you look, so the point is, when does it start? Leave your system to relax at its lowest energy state. So you just leave it there to oscillate. Okay. Eventually, it will release all its energy. So it will reach its lowest possible energy state, which is the.
Treating the electron with harmonic system.
So I'm treating the.
The electron with harmonic system.
Right. So if you remember, it's like a plasma. It's a plasmon. Yeah, exactly.
So I don't think it's the individual electrons themselves.
Yeah, it's like in a superconducting state, they all start here just one part.
So
I'm not
yeah.
sure.
So if you just wait for your circuit to stop, okay, it will reach its ground state. And in the ground state, it cannot not oscillate. It cannot be static, your circuit, right? So even in the ground state at 0 temperature, your current is going to be oscillating like that. So this is not the right picture because
You have the metal,
yeah,
and then there is something called free electron belt.
free electrons belt, correct?
There's this thing in our feet.
Exactly. Exactly. So actually it becomes superconducting, so but it's exactly the same thing. So what happens is they pair into Cooper pairs, and then it's pairs of electrons that move. But it's the same thing, exactly the same thing. So then you have you have your conducting band, and these electrons are basically moving as a circuit, and they're basically moving collectively. Like take an LC oscillator, just a normal circuit. That's what would happen, right? What happens in quantum mechanically is in your initial state, your current is never going to be, is not going to be, this is your oscillation in your circuit, correct? Right? So now you have to imagine that this is happening, but it's happening in this direction and in this direction at the same time. It's basically what I meant by, when I start talking about, I make a comparison. Now my current I is actually delocalized. But it's neither negative nor positive. It's actually moving like this. Positive and it's negative. So that's why it's.
Electrons to vibrate out of phase.
Say again?
Suppose they are like in the metal band,
Yeah.
even in the ground state, they can maybe vibrate in the opposite direction so that they don't go in one direction.
They'll be oscillating with all possible phases at the same time, right? So if it's oscillating like this, this is like oscillating with a single phase, correct?
That is just the phase becomes stable.
This is like a single phase, but then it's not this. It has to be everything. It's kind of all the same. In the same way as here, your oscillator is oscillating like this, but it's not oscillating like this. It's actually oscillating everywhere at the same time. In some sense, just delocalized. It's just a mass. It's everywhere at the same time. It's just a blurb, like a delocalized blurb of mass, of probability. Yeah.
To register as a current, it has to flow at any cross section, something should cross. To register as a current.
To register as a current, say again?
To register as a current, at any cross section, some charge should cross.
Yes, yes, but it could also be zero current. Zero current also exists. In the superposition, in the quantum state, there's also zero current because it oscillates with all possible currents, right? So this means here, you see I have some wave as zero current, which means there's a certain probability there's zero current. There is a certain probability there is this amount of current. There's a probability there is a negative current. So basically, the value of your current is probabilistic once you get into quantum mechanics. Just as the location of your mass is probabilistic, or the location of your electron in the box is probabilistic, right? That's the analogy. The current is probabilistic in the same way as the location of your electron is probabilistic.
Current compared to 1 ampere.
Say again?
How small is current compared to 1 ampere?
Okay. Yeah, I don't know that. How much it is. See, it has to be the energy of your oscillation has to be h times the frequency. So h times your 5 gigahertz. So it's h is 10 to the minus 35, 30, 31, and then. So compared to 1 ampere, I don't know that.
If I'm correct, your question is, you agree that the Edison circle is giving you a harmonic oscillator. Is your question, why is it a quantized harmonic oscillator? That
Why is it a quantized harmonic oscillator?
then it's a harmonic oscillator. That is right. But
Because that is a classical thing. We learn that, right?
Right. So, I mean, why things are quantized in the same way?
Is it because of the Cooper pairs? They are actually having some kind of specific energy levels. It's not a distribution. Is it that reason that it is coming?
No, it's not about the granularity of your current, of your Cooper pairs of that. That's not that doesn't come into the equations even.
I think making it superconducting is the point where it starts to behave quantum mechanically.
Well, superconductor doesn't give you any quantum.
I'm telling that the process in which we take the
Yeah,
qubit
yeah.
to make that photon go to that superconducting state.
Yeah.
That's where this quantum properties start to. I'm not saying superconductor is it's in itself quantum in nature.
Mm.
But this circuit will start to exhibit its quantum nature when it is going to superconducting state. That's what I'm guessing. Or else, I think that is where the
Because of the separation, it won't be able to behave quantum mechanically at all before you get to superconducting state, right? So it won't be.
This analogy is there if we start quantizing XP. Here we have phi and Q.
Yeah.
Here we have the currently conjugate variables phi, the inductance phi and Q
Yeah.
as the variables, and then we quantize and we write the same relation like we do for harmonic oscillator.
Yeah, so mathematically it's obvious there are same Hamiltonians, but to people who don't deal with Hamiltonians, it's hard to explain directly. Fundamentally, I don't know if there is a reason why two things that behave like harmonic oscillators just behave the same quantum mechanically. Just turns out that it's the same formalism and you quantize in the same way and you just end up with the same quantum behavior. Hmm?
Mainly can picture it as a linear flow. Because I mean, it appears that all the electrons in the band must behave in a similar way.
Yeah, they're all behaving in the same way. Yeah.
and what one writes on the Hamilton, then if you
Say again?
write on the Hamilton,
Yeah. Yeah.
identify the quote unquote potential term.
Yeah.
So it should be I square.
Yeah.
Physically. So in some intuitive sense, what quantizes the harmonic oscillator is that you have certain volumes, and even though the wave function is not zero at volts, it doesn't go beyond that.
Yeah.
So if we can find out like some physically like some electromagnetic reason why that I square gives us a one, then perhaps that might explain why it's quantized.
Yeah. It's a good point.
So
but what would be the potential? It's not obvious to write that in the electric circuit. Half Li squared, yeah, half Li squared. But why does that play a role of confinement? That I'm not. But that's a nice analogy. Yeah, the fact that if you find the confinement, moment you have confinement, you have quantization, right? That's what I was trying to say in this talk also. So yeah, if we can find.
This works with higher sizes as well. It doesn't have to be very small.
Yes.
So this will exhibit.
It does work. Quantum mechanics works with higher systems also. But you're right. The point is that all the electrons are locked. Yeah. They're locked in this BCS superconducting sea of Cooper pairs, right? And so the superconductivity is they all can.
Probably say that we can write an average state for the whole thing.
Yeah. So actually, it is basically all the electrons are moving as one. That's maybe something because superconductivity is this. They all get locked and they cannot just exit and behave by themselves, right? So because of that, they don't see even the matter. They just flow through it without friction. It becomes superconductivity. So it's like a block. And because it's a block, it actually, maybe that is why, we can actually.
Something that I don't really understand. Is it similar to what Einstein condensate is?
Bose-Einstein condensate?
Yes.
No. No, the superconductor is not a Bose-Einstein condensate. It's a similar idea, but it's not a condensate. Yeah. Yeah.
Yeah, but like it's physics.
Oh yeah, no, please.
So, in the talk description, you mentioned also just sort of the promise, but also the limits of quantum computing.
Hmm.
Because to an unfamiliar audience, there's always this idea of quantum computing is going to come along and solve
Yeah.
all of these problems that in our current forms of computing, it's going to be this massive leap.
Right.
What are the prospects of that really?
Of getting a quantum computer, right?
Yeah,
Yeah,
or what
like-
it can do.
What it can do.
They don't
Yeah.
know.
So in order, basically, the usage, it's going to be useful when it can go faster than what do a classical, computer can do, and that would be, having probably right now that be having 40 qubits that are working perfectly. That would already give you something. It would work as a quantum simulator, but it wouldn't still not be so fast. Okay, the problem is we're still not managing to. We kind of starting to manipulate the quantum properly. The problem is this scaling. So when you put too many of these together, they start to talk to each other, and that's what he was saying here. So basically, each of these circuits, they will have some fields. They'll create some fields, and each of these fields are going to talk to other circuits, and because they talk to each other. So you have to put some distance between them. You have to change their frequencies. It's very hard to actually arrange them. So that's one of the big challenges in terms of scaling up, putting more. One of the solutions is to create more chips and divide the qubits in different chips. But then again, you'll have some losses. So the information has to travel. So this becomes harder. So the more you create different chips and everything. And to actually get something useful, you would need something like 100,000, 1 million qubit to get to decryption, RSA decryption. People talk a lot about decryption, how quantum computation can create RSA be used for decryption of whatever your credit cards and everything. So the point is that is very, very, very far away, right? So before that, people might be able to start simulating molecules in the same way that Feynman had in mind, that you can actually map the complexity of your molecule on your quantum computer. In there, you can basically deduce the properties of your molecule, whatever, and then find, invent drugs or things like this by just simulating your molecule. So yeah, we're still very far from something. It's still not from the close future.
Actually, building a quantum computer is a very ambitious task. There are intermediate applications which are much more approachable. Like one is within communication.
Yes, that's true. There's quantum communication. Yeah.
States to very long distances now. And there is something called, I think it's called quantum sensing, where we can do very precise measurements within the areas. For that, we don't need to suffer through trying to bring so many qubits together.
Yeah.
So with smaller systems, we can precise tuning them. Yeah. Yeah. So we are a very steep target with this.
Yeah, that's true. That's the steepest target. Quantum communication is closest, but it's not computing. It's a different quantum application. Yeah.
You can couple your small quantum system to a proprietary quantum measure, and then you can make the moment of another, and that will give you very precise values.
Yes. It's a bit complex. I can discuss at some other time also, teacher. Yeah, it's exactly like he says. You add another device, and that qubit is going to, depending on its state, is going to affect your other device, right? Slightly in one way or another, and then you can measure that property on that device, and there where you measure your state. You have to.
It's always a problem
Yeah.
so I'm just thinking from that perspective.
Yes. Yeah.
Okay, we can thank the speaker.
You can say it in everything.
Thank you.